some more people. So I guess I will get started. And so last time we kind of talked about like how to visualize some of the CNN and CNN model, trying to understand what's going on inside the model there. And I guess by the end of the class, we talk about two different approaches, actually a couple. So one of them, of course, you can just look into just the weights there, because if you are in the first layer, you can just look into the weight. Let's see. Start from the beginning. But if you look into the high layers, then if you look at the weight alone, basically the weight doesn't give you much information there. So instead, like there's a couple ways, of course. For example, you can do some occlusion experiment, and we mentioned using T-SLE in the last layer, trying to group. Basically, you look at the last layer. You look at think of that as a representation vector. So anything that's close together, you just kind of like put them together. Like of course, that vector starts in a high dimensional space. You projected that into a low dimensional space, like typically a 2D space, using T-SLE, and then like in that way, like each of these points will correspond to one image. So images that are kind of like have similar class will be together. So we'll have a very kind of have a pattern like this. Like if you click into this link, like you have each of this image close by is basically have in the same class. For example, you have dog here and dog there, and so on and so forth. And we talk about T-SLE, and also like the other two ways to visualize that is one is like by backpop, but kind of slightly modify the backpop. We have a guided backpop or using a deconvolutional approach. Then you just look into one particular layer, so you have here, and then like backpop the image or like the information back to the original image. Then you can get nice picture like this, like in different layers. Like here, like in different layers, you can have different kind of different kinds. Basically, you can see like deeper layer, you have higher level features, right? So, for example, in layer 4, you can see this is an input, is dogs. So you can see like this, more or less you can see a dog face there. And we also look into like using optimization. So that's the other approach. And in terms of optimization, you can fix one of the layer and trying to find the image to optimize, in the sense that the image should match with whatever you want in that layer there. Or of course, you can just fix one of the coefficient in that layer. In that case, for example, if you fix that for the last layer, then it will be more or less like you can fix in the last layer, let's say that will give you class of different objects, right? So maybe you fix that, okay, I want to have one of the class is a computer keyboard. I said 1 and all the others will be 0 there. Then you try to find an image that optimize this output there. And of course, as mentioned last time, like if you just trying to generate random image without any regularization there, then most likely will get garbage. So in the past couple of years, people just try different kind of regularization to get good images. So this is the earlier one, like by Cisawa, like 2014. Then you look at better and better with regularization, just get really good result. Actually, the last one, that's one I like to mention. I think I made a mistake last time. So when I describe this thing, what's going on? I think this is a 2016 paper. So they use a generative network. We'll go into that like later on, like a couple, maybe, I don't know, 4 or 5 lectures later on. So this generative network is basically you train this network and then giving different inputs, you generate different images. And if you train this network well, like whatever input you give it here, it will kind of generate an image kind of reasonable. So what they did here is like they pre-trained this generated network and hook it up with this DNN structure here. And then at the end, for example, I like to generate a candle. I'll set candle here. Now what I train is like I try to train the input here. So n by n to n. So I want to change this input here. I fix everything else. So once I train this thing, for example, like I fix this candle, like giving many candle images, and I train this, and eventually I find a good code for that. Then next time I can just plug in this code, and I know this will generate a candle, for example. And then this can give really amazing results. Like this is a voice. Okay, because I remember that like this. Yeah, anyway, I'll go back to this later because when we talk about generative network, we'll talk more about this. So, okay, what we are going to talk about first is talk about, well, actually, did we talk about this already also? Like, I think we did. So, it's deep dream. So, what they did there is they have a neural network, basically pre-trained also, like, you can have like AlexNet or like Google Net and so on. And then like what they call is like I try to dream in a particular layer in the network. So what I mean is that like if we dream there, basically just we try to reinforce the signal there. So therefore you see like this is a code slit there, and the main line here is something like this. So what they did is just when you backpop back, you just make the gradient there proportional to the current signal there. So therefore, like essentially, you will just reinforce whatever you are seeing there. So then, if you do that, like you have images, just give you like very interesting patterns. And depends on like which layer you dream, you just have different results. For example, like if you dream in the later layers, you have like some animals coming up because like in that layer you just have like very high level representation. But if you go to like lower layer, so you will just get patterns. So and you can do multi-resolution things. Then you can work on high definition images and have like lots of interesting pictures there. Depends on your data set. Like this one they train on ImageNet, then you just have lots of animals there, dogs, cats, and whatever. But this one is another data set, have lots of architectures, so therefore get something like this. And that we stopped there last time, so we'll continue like what we talked about. So first thing I like to talk about is word called Lewd style. So the idea is very much similar to what it's again like we're trying to take advantage of the neural network to make some artistic pictures here. So what we want is we have an input image and we have some style image here. So our target is like can we create an image out of this content but have this style? So basically combine this content of this image with the style of this image and get something like this. And this is for real. This is really cool. And you have like different kind of styles for this image. And how did they do it is actually kind of magical. The idea is that, okay, for the content part, it's easy to understand, right? Basically, you have an image you put into the network. Then if you look at some of this layer, it will correspond to the contents, right? So for example, you fix the one of this layer here, and you just use approach we mentioned earlier, backpop and whatever, or like optimization. Then you get an image, actually typically use optimization. Then you have an image kind of closely related with this content. But in terms of the style, what happened is that like the styles of the image actually can be think of simply. Yes. Yes. Hi. You cannot hear us. Let's see if like I can hear you, but let's see if I it seems like mute, but can we unmute? Oh, okay. I pressed that earlier, but it didn't. Okay. So okay. Then in terms of the style of an image, what happened is that like you can imagine it's kind of magical if you think of that. The style you can think of is really the correlation of a pixel from one place to another. I don't know why, but statistical wise, maybe you can for example, if you have a pattern, if you have something like I don't know. I guess I give up. I cannot give you a very good explanation for this, but it turns out it just worked. So maybe I will just explain like what's going on here, but instead of trying to give a rationale for that. The style, as I said, will be just the correlation matrix or the graph matrix. So basically, you have an image coming in, then you take the look at one particular layer. Let's say maybe this will be a little bit better. So let's say we look at one particular layer. You have some outputs here of that layer. Then we look at the cross correlation of each of the coefficient across the layer. So for example, like if this layer have 10 coefficients there, then you can compute the cross correlation matrix, right? Of course, it will be an estimate if you just have one sample there. But if you have lots of sample, then you can compute the cross correlation for that, right? So then with that, then you fix the cross correlation there. So you go for many inputs there. You compute the cross correlation for that cross correlation matrix there. Now for the content, again, you may fix one of the layer there. Like we fix one layer here. So then this you have a joint cost now. So basically you start with some random image as input. Now you try to fit your output such that in each layer, this one, if you compute the cross correlation, will be the same as the one expected from this style, and also like for each of the other layers will be just similar like this. And then also like in one of the layer, for this layer here, the features should match with the features of the content image. So, and if you do that, then something magical just happen, and you will get the combination will be just like that. So, yes.
If we change the content target in different layers, like right now it's a yellow layer.
Yeah.
If we change it later to the pink layer, what's going to happen to our output? So is that like the D3?
You can even combine that. So the D-train basically you set the gradient as the current input, right? So you can add that as an extra cost also. You make the gradient look like the actually that's one of the example is like combining that. Let's see if I can find this. Yeah, I think this is one of the example. They combine the style, the content, and also like the digit kind of cost function, cost also. Then if they combine them, they have something like that. So have that style, have that content, and also kind of dream about something. But okay, in terms of your question again, like what's that again? Like
if we change the output layer, right here is the yellow layer. We change it early to.
Oh, you mean like this one? You change into this different layer too? Yes, it will have different effects there, but I honestly I didn't try it myself, so I cannot. But if you want to play with that, like there's lots of source code. One of the earlier source code is by I think it's by Justin Johnson, and actually I played with the source code before, but I didn't play that far into. I just tried to run it, so but it's actually really amazing, and you can do simple trade-off also. For example, like because you have two costs, right? You have the content loss, basically how close to the content image, and also you can have the style loss, is like how close to that style. Then you can like just have a parameter to tune. You can weight more to the style or weight more to the content, and you have effect like continuous effect like this. Yeah.
Go back to the
yes.
So when training this network, so the parameters in the network is fixed, and we will train the pixel values in the random image.
Yes.
Right?
Yes. Yes.
So the last function is to maximize the coefficient, correlation coefficient.
Right? Yes. So it's matching. Basically, you get into this. You put in an image here, then you can compute for this layer. You compute the correlation coefficient for this layer, correlation coefficient for this layer, correlation coefficient for this layer. Then you put in this content here. You have another set of coefficient. Now you store the coefficient for this one. Then now you just start with a random image. Then you try to match the representation here, compute the correlation coefficient, and try to match this correlation coefficient with this one. Yes. That's the coherence matrix, basically the coherence matrix of this one with this one, something like, and this one with this one, and so on. So it's very simple. Actually, the idea is very simple. Then, but it just works amazingly. And since then already, like this is like 2016. That's I guess early of 2015, 2016. But that's already lots of follow-up work from here. So for example, like this is another example like how you can fine-tune that, because if you have this style image, you can, if you use a lower resolution style image, you will have different styles also, right? So if you look at this one, this basically is just what they did here. So if you use a original image size to compute the style, you get something like this. If you first downsample the image and compute the style, or compute the cross correlation coefficients, you get something like this. So you can just play with different effects. And of course, you can even do like multiple styles. So you just combine, give two scores there. So just think of any combination. Basically, I can imagine, for example, you have multiple layers to compute the coherence matrix, right? You can have one layer for this style and another layer for a different styles, and you can get different images. And they all looks amazing, basically. So one drawback here is that the approach I just mentioned here is pretty slow, right? Because you go through this optimization, trying to you basically it's like training a little lecture more or less, like, so you do all this backpop and then gradient descent, and it's pretty slow. But immediately there's solution already. So the solution is because ultimately you just want to have an input that kind of let's see. Yeah, okay. You want to have an input have this style, right? So what you can do is, instead of trying to train this image here, you train this lateral instead. So what you have is like now you have the style is fixed, like as before. Now you have an image coming in, maybe like different images, like many different images, content images. Now you're trying to train this neural lateral such that like those metric score is satisfied. And once like this whole thing is changed, so you have now a feed-forward neural network here, and then you can just forget about all these things. So, and you can now put this network in your cell phone, and then when you work a feed-forward network, basically just one round, right? It's really quick. You put in an image, do a feed-forward network, then you get this result here. So then, basically you can do something real time. And I think you will be too. So maybe you will have some idea to keep changing this thing. For example, like one thing you may want to change is like, how about I can have like another dial to have different kind of styles each time. And unfortunately, someone already did that also. I think like either this work or let's see. Oh, okay, this is still the last one. So yeah, this is another work basically, but this is all there's some result for the work by the Stanford group, and actually at the same time another group in Russia also have similar idea, and they published that, and actually they use a different kind of normalization to get a little bit better result. I didn't go into detail for that, so a bit about this paper, so I'm not going to comment on this now. But as I mentioned, that's another idea that you can just have one network but many different styles. So basically, what you can do is think of you train the network, but you can also train an extra. Maybe it's better to go to these slides. Maybe it's easier. So you can think of, okay, I train this network, but I can train a different inputs, right? Maybe like I have an input here, and I have a style here, and for this particular input, I will correspond to this style. Now I switch to another style, and I try to, let's see, am I making sense here? Maybe I'll go back to these slides if like you guys may be able to help me also. We can study it together. So this is what they did here. Let's see, using conditional instance normalization.
They just save different mean value and errors for different scales, for different styles.
Yes. Yeah, it looks like so. Maybe we'll come back to this next time. But yeah, I think, or actually, anyway, you can pick up the paper also. Like, if you are really interested into that. But what I'm saying, like, this goes just really quickly. This whole area is just 2 years ago. Then like they already kind of try all the different things, and of course, because there's lots of application for this way. You can imagine like you have all these cell phone apps will be very, very popular to change photos into different styles, and people love it. And yeah, and So anyway, I would just let you to look into the paper if you are interested. And one last topic I'd like to talk about visualization is that is some weak points of CNN, or like actually it's like same for all linear model. Basically, it's very easy to fool in models, linear models. For example, like if I have this originally classified as a school bus, I can make a slight distortion to make it like a ostrich. Is that how to pronounce that? I want to know.
Ostrich?
Yeah, ostrich. Yeah, yes, and yeah, basically you can make anything to look like an ostrich. As long as you create some distortion, like align into. But of course, I for lateral images, but I don't know. I don't know what's the application for that. Like maybe if you can break into the system somewhere and get into that video or images, maybe you can really make your face close to some other ones, like make the system think that you are someone else's face or something like that. But you can imagine why this is so, right? Because basically you have more or less like actually I already this the M. I don't have very much slides is explaining that, but if you think of I guess I erased the slides. I thought it's useless. But actually, as I mentioned, you can easily imagine that, right? Because I think of I can write it here. Think of like, let's say you have two classes in some high-dimensional space, and you have the boundary somewhere. So if you are very high-dimensional space, of course it's 2D. It looks like you need to change a whole lot to go to here. But you know which direction you need to go from basically from one class to another class. For example, if in the last class, if I have some basically some classification that is just going through some linear layer that some AX is bigger than equal to some threshold, or maybe bigger equal to 0, then let's say X is your input, like eventually, if it's bigger than equal to 0, you have a cat, and then like otherwise you get someone else, like not cat or something like that. Then I can just modify this a little bit, right? It used to be, let's say AX, A transpose X is a cat, therefore it's bigger than equal to 0. But I know that I can modify X a little bit by X change to X minus delta times A, right? My delta can be pretty small, but then if I do that, like my new X, let's say this A pi, X pi here, then A transpose X pi will be equal to A transpose X minus delta A transpose A, something like that. And of course this will be positive. And if I have a big enough, it turns out it doesn't need to be very big. You will shift your boundary, shift away from the boundary, like before to be bigger than equal to 0 to like below 0. And that's exactly what's going on. And that's some other like interesting thing, that you can just generate random images and say, okay, this is Robin, this is Cheetah, and something like that. And the neural lateral will have 99.6% confidence saying, okay, this is an armadillo, something like. And more example like this. But one thing I'd like to mention, that this is not something new. This just happened to all linear systems. So if your last layer, you're not exactly linear. If your what I want to say is not, you have the activation function is not near at the end, but basically the decision that you just made beforehand is like linear, right? So you basically have a representation layer in the last layer, something like that typically. Have the last layer. You this layer input, let's say this x something like that, you have some go for a lateral, right? So and you, for example, if you do just a binary decision, then you just basically multiplying some weight vector, as I mentioned earlier, maybe some A transpose, then you will make a decision here, right? So you have a nonlinear activation here. In this case, this nonlinearity will be just bigger than or less than equal to some threshold. And whatever you have the last layer of making decision have something like this, then you can easily fool the lateral basically. So therefore, like, it's not something only restrictive to little lateral. Basically, it just happened to all essentially, I mean, virtually all like machine learning system. Maybe except if you have like secondary decision, maybe if the last layer, if some secondary decision, let's say like x square something like, or I don't know, this is x transpose, maybe you have some terms like this, or you have x transpose times some a b whatever, then that may be a different story. But typically it's very hard to change something like this. So therefore, like I guess it's interesting to think about this, but it looks like there's no very good solution for this issue here. And again, this is not a big problem because unless you know this last layer was the coefficient here, you are not that easy to attack this system. And even though you know what is this, it's hard to guess like what you should change the input such that the output in the last layer will be something like x plus a delta a, right? This is difficult to predict. So unless you know everything about this network, then it's not easy to attack it really. So anyway, so that's the last thing I'd like to talk about this. So and I guess the next thing I like to talk about was the time here. I'll talk maybe half of it, or like let's see. Yes. So I like to look into some CNN applications here. So of course CNN started as like for image and basically for computer vision, right? So the applications I'm talking about today are all like computer vision related. So I kind of shamelessly borrowed basically the lecture slides from the Stanford course. They did really a great job this time. Actually, they did a great job last time also, but this year the slides is actually even cleaner. So we'll look into several applications here. Semantic. Sorry. Let's see. I still prefer the web. Web pen here. So semantic segmentation, object localization, detection, and instant segmentation. We look into recognition already, right? Because basically the recognition problem is more or less for computer vision is considered solved maybe. So nowadays people work on computer vision with neural network, typically look into other problems now. So let's start with this is like, so far we have, this is like, we have some images, and many images, and then we have some neural network here. I think there's an Alex lab here. So you train the network, right? And you train it end to end, then you have a good network here. And typically you have this network here, you can use this network to help you to work on all other applications as I mentioned here. And so this are basically the computer vision tasks I mentioned earlier. So semantic segmentation means that like you have an image, you want to figure out for each of the pixel what that pixel correspond to the object. For example, here you have these are the cats here, cats pixels, and these are the grass pixels, these are the trees, this is the skies. And then like classification plus localization is like you want to classify the image and you also want to localize it. And typically like you just have like one, when we say classification plus localization, you just have one key object there that you want to classify. And for object detection, you have a more complex image that have different classes there. Like you have dogs here and also cats here. You want to both like find where basically you want to locate all these animals, like all these objects here that you know that you're interested in. And then instance segmentation is the most challenging one, that you basically want to find the object there. It's like the object detection, but also like in the semantic segmentation, you want to find in this object, like what's the boundary there, like which the pixels there is correspond to the dogs, and which dogs, and so on. So as you can say, the difference of this one and this one is like you really can separate all like individual objects there. So let's start with the semantic segmentation. And there's some more example here, like this one. So if, as I mentioned, like here you don't separate like different objects. Like here is like kind of like a perfect result for semantic segmentation. You have cloud here, but I don't know if this cloud is actually, I cannot see how these two clouds are actually separated. The way to do it, like a very simple approach, as you can imagine, is okay. I can take each of the patch I'm trying to do like recognition, right? And then I will say I take this patch here, trying to recognize. Then the pixel in the middle and the center pixel, I will say if this recognized as a cloud, then I will say the center pixel is a cloud. And then I just slide through the entire image and repeat that. That will work, but it will be really time consuming, right? So you it's extremely inefficient. But one thing you can imagine is that like each time you take a patch, you go through the CNN and so on, and actually if you shift the things, right, you first do this patch and then you shift to the next patch, you have many coefficients basically overlapped, right? There's lots of ways of compute. So what we can do is like actually we can combine all these once. So one very intuitive way is let's just train a CNN to do this, right? You have a consecutive CNN, and then in the last layer, let's say I have CNN like conflict layer pattern one by one, and at the end, let's say if I have W class, I have C classes there. In the last layer, I may have like C different filters, and then I can just do a softmax like at the end, something like for each pixel I would design like okay which one is likely this pixel, basically this pixel will correspond to this corner or something like. I think like this pixel, if like this coefficient is biggest, maybe this coefficient corresponding to the sky, then I'm doing a great job, something like. Or actually it should be 3 there. Is this clear? Like this is a very simple concept, but this is not the way you're supposed to do also. The problem is like again like that will have loss of compute, because like you do CNN, you basically have a filter. Each time you just go through the entire image, right? So maybe in the future it's okay. Like at this moment, the current amount of like computational power that we typically have, this is still like too much. So one way we can do it is like a more reasonable way is to do a kind of like a, I don't know, telescope. I don't know what kind of, how do you describe this thing. So I just go for a downsample and do an upsample again. So of course, like downsample, we are all very familiar with that because we have like mass pooling and so on. Like all these are downsampling. So upsampling is a little bit new to us. We never actually we kind of mentioned upsampling last time when we talk about guided backpop and like deconflet. So the idea is quite a bit similar here. So when we do upsampling, then let's say uppolling now, there's different way to do that. Like for example, you can just do a Lewis label. So for example, if you upsample 2x2 to 4x4, you can just like fill all of them basically, just a very simple upsampling. It's almost like a conical product here. So or you can do a so-called bed of layers. So what's going on is like you just pick you just upsample one of these 4 coefficients here and fill zeros there for the rest. And you can do a little bit more intelligent way is called mass unpolling. That you basically use the information that you got earlier also. So in the earlier layers you have, because you first go down and then you go up, go back up, right? So when you do the downsampling here, you do the mass polling here, what you can do is you can remember where the element you actually are the maximum. And then when you do the mass unpolling, you only set those elements to non-zero values. So this typically give you better result. And you can also wait a sec. Yeah, where am I? Okay. Yeah. So besides mass polling, like one way you can do downsampling is that you can just do stride, right? For example, like this is the stride one. You can downsample your input like by doing like let's say stride 2 on the input, right? So then like now we will have the same problem. Like if we downsample this, we need to upsample that back, right, later on. So then we need to decide how do we upsample this. A very kind of a natural way to do it is simply go for a so-called transpose convolution. Basically, you have this you have this convolution coefficient convolution filter here, right? So when you do downsampling, you are doing a dot product of this filter with the inputs here, right? Now, if you do the opposite, you basically just like multiply this thing with the filters and fill in the values here, and then you continue to do that. And when you overlap, then you just add both the contribution from this wet filter and also from this blue filter. Is that clear about that? Maybe the 1D example is more clear. So if you have filter like this, you have like input A and B, then you have something like AX, AY, and AZ here, then and here BX, BY, BZ here. So then you just add them together. So that's the transpose convolution. Then with this, then you can again do spat pop and change this model, right? So you have this model here. You just put in input, put in output here. By the way, what do you think? How do you have this ground truth here? How do you get this ground truth here? Actually, it's the most primitive way to do it. It's like by human. You just go pixel by pixel and plot like which one is like cat, which one. So therefore, it's extremely expensive. But it looks like it's we're not going to get it. But at least the great thing is like we just have like infinite amount of storage nowadays. So whatever people did this like point by point human labor, pixel by pixel human labor data sets, they will be just there forever. So I guess yeah, but it's expensive. But I can imagine that like companies like that they do this most likely are not going to share all this like data set like training set to other people because like it's really very expensive. So what I'm doing with time, let me just do a little bit more. So the next problem is like to look into classification and then localization. So here like again like it's simpler than this one. We are just assume there's one single object there and like trying to recognize one single object. So one way what we can do is like we pre-train some neural network using classification, right? So we pre-train, for example, AlexNet here. And in the last layer, let's say we have a fully connected layer, we can just kind of use this to connect to a neural network, maybe just a small network here, and to give out two different scores. One is like a score for one is just the normal like classification score that basically what we already have like when we train the AlexNet. The other one is like trying to build a kind of localization score. For this one will be like a localization will be like a a regression problem here, right? So here I should get instead of like one classes, I'll have like many values here. So I try to regress into like X, Y, W, H here. And now then we just train this model, basically train the, or like if you want to be lazy, actually you already have AlexNet here, right? We can just train this part and hopefully like things will work well. And then of course you can also like if you have lots of data you can try to use the both loss here and train it the whole network again, and then it may give you like better results. And so in this case like you train both of them, you have a multitask loss, and basically it's a weighted sum here that the weight you will be like some hyperparameter also, like you want to kind of that one you will just need to figure it out. Probably you need to train it many times. This is one interesting example, like just a side note, a very similar idea to combine like both like a classification course and also a regression course. Here like it's trying to basically classify the joins there and also like find the join location. So if you find the join location, it will be a regression problem, right? So if you combine them, then you are able to find the basically the entire skeleton of someone, and then you can use that basically to estimate the pose. And that's like this. So for multi-class, so then let's say if I have multiple objects, let's look into this problem now. So if we have multiple objects, as you can see, like this is just a chart showing like before neural network and after neural network, like how much improvement we have. And for detection problem, by the way, like I'm not sure like how many of you heard of like the mean average precision. This is the typical metric to for detection problem. For example, like you want to kind of see like the detection problem here. I'm thinking about like document Yeah, actually, document retrieval. I'm looking for that word. I'm sorry about that. I always have problem like thinking about word. That's also like a metric typically used in document retrieval. So in that case, would be like you have a large number of documents, right? And say I give an entry, for example, Trump, and then I want to pull out all the documents. I have another entry, for example, Obama, pull out all the documents there. And then how do I know like my result is good or bad? Then that would be like depend on recall and also precision, right? Precision means that like how much time, approximately how much time the things I got. He said like this doc is a document of Obama. It's a document of Obama. Will be precision, right? If 100% precision will be every time you say like this is a document of Obama, it's really related to Obama. Then the recall will be like inside maybe there's like 100 documents is related to Obama, but maybe only pull out like 50 of those. Then the recall will be only 50%. It's not that great. So typically you have a precision and recall trade-off there, right? If you have one thing is precision, that's 100%, and there's a recall here, this is also 100% here. Then it's difficult to have like 100% precision and 100% recall. So you typically will have like either curve like this or like that. So anyway, so you will have a trade-off like this. And if you look at this 100% here, so the mean average precision, or actually maybe I should say this is a recall, this is precision. So the mean average precision will be basically the area underneath this thing. So then naturally it will be a metric to judge like how good your detection algorithm. And why is mean average precision? Because you have multiple classes. So you look at like the average precision for Obama, average precision for Trump, and average precision for Hillary, and so on. And then you take the mean, then you use that for estimate to gauge how efficient your algorithm is. So and then like you look at that like before that is this, and after deep neural network is like this. And of course like if we have multiple class, you can imagine one way we can do is also try to combine classification and regression. Each time you find a class, find an object there, you're trying to also find the bounding box for that, or find a regression for that, for the bounding box like x, y, and also the width and height. But of course the difficulty here is like because we don't know ahead like how many objects are there. So it becomes quite a bit more complicated, like how you build a network, you don't know like the size of output there. So actually people even try that. That's the YOLO things. I just assume there will be so many of them. But yeah, I find actually maybe I can, instead of going through the other class, maybe I because it's near off time, so maybe I start with YOLO. So the YOLO idea will be okay. I will just partition the whole images into many grids there, and then I'll assume like okay, for each grid it's likely to have like so many, maybe one class because it's a small grid, right? There'll be one class there. I'll just assume, but also I will allow some flexibilities that like I'll try different shape of the region there. So inside this grid, I may, for example, in this simple example, I try a long long rectangle or like a flat rectangle or like a square there. There will be like more combinations like in the actual implementation. And then each of them I will try to see like if there's an object there. And then if there's an object there, also try like if that I also try to modify this bounding box. Basically trying to regret like do the regression to find the adjustment for the location and also the width and height. And that's the idea for the YOLO. And that's something very similar called SSD also. This is pretty fast compared to this other approach I'm going to talk about next time. Any questions for that? Right. So in this case, like as you can see, the number of outputs is fixed. So I assume that you can partition the image into 7 by 7 grids, and then assume that each of the grid like they have like 5 different base boxes, and let's say I have C classes, then you can compute the actual number of outputs supposed to be, and then you just build a big network and expect the output to be this big things here, and then you put in the training, input training data set, and you just keep training, and then yes, that's YOLO or SSD. Yeah, and SSD is more or less similar also. I am not sure if Tosa have any question. Yes, that's okay. Yeah. So if not, maybe we'll just stop here, and then I will come back next time, and we'll talk about other way to do object detection.